Okay, good morning and let's get started with the lecture. This is our last lecture for this series that I do. So last week we looked at an example. We started looking at an example with feedback amplifiers. This is the circuit that we had. I had two stages, both common emitter stages with NPN transistors with a feedback resistor connected from output to the collector of the output stage to the emitter of the input stage, right. So we started looking at how to tackle this, and then we during the last class we did the step 1. That is basically identifying the topology, right. We identified this topology and we did this by first identifying where the feedback element was connected, right. So this is the feedback element, it was connected from here to there, right. So that we identified, and then in identifying this we followed kind of an algorithm to figure out what is the topology. I said in order to identify the sensing networks, whether, in other words, whether the output is a voltage or a current. If the output is a voltage, sensing has to be in parallel like a voltmeter, right. So sensing has to be parallel, so we call it shunt sampling. In that case output is a voltage, so we name it voltage if the feedback element is directly connected to the output voltage terminal, and we observe that this is the case here. This is the output voltage and we have one end of the feedback resistor directly connected there. So therefore we identified the mixing network as a shunt or voltage voltage sampling, right. So they are sampling it out. In other words, the output was a voltage. Second, in order to identify the mixing network, if the feedback element was directly connected to the input, then that's in parallel with the source that we know. We combine sources in parallel for currents, right. So therefore in this case we don't have this feedback element directly connected to the input, so therefore this is not a current input, or in other words it's not a shunt mixing circuit, right. That also we therefore the mixing is then should be a voltage, it's a voltage mixing because it's not current, it's a voltage mixing. Voltages we mix in series, so therefore this is a series mixing. Output is a voltage, so therefore we sense in shunt, so series shunt. So this is a series, so this is connected in series, this is connected in shunt, so series shunt topology, which is the same as the other way of telling this is the output type, which is the voltage, and the mixing type series. This is the same, okay. In both things this is the same. So output, this is shunt, is the voltage, right. So in two different ways. So we decided that, and then we identified the output voltage as X naught in general terms, and and the feedback voltage we identified as this, that is Vf. That is Vf XF is equal to VF, and X out is equal to V out. So, we identified that, and then we also calculate the value of beta. So, we identified that sampling network looks like this. Right. So, Vf is this, V out is this, where beta is Xf over X out, Xf is my Vf, X out is V out. This is equal to this voltage divided by that voltage. So, therefore, this is 10K, this is RF, and this is 100 ohms. This is RE1. So, RE1 divided by RE1 plus RF, that becomes 100 divided by 100 plus 10K. So, this was roughly equal to 0.01. This is where we stopped last time, right. So, this is where we stopped last time. So, we know the value of beta. Now, the second part, step 2, this is very important. Step 2, we briefly discussed about it, but we will start from there. Do you have any questions up to this? Any questions up to this? Right. So, step 2, our objective of step 2 is to draw this feedback amplifier without feedback, so that we can find A, R in and R out without feedback. So, that our objective is actually ultimately find amplification A, the gain, input and output impedances with feedback RIF, ROF and AVF. But we know that if you know A, Ri and R out without feedback, simply multiplying by 1 plus beta A, we can obtain the other quantities. So, therefore, the objective of this one is to find or draw a network without feedback. However, that does not mean we can ignore the effects of loading due to this RF. This RF is there anyhow. So, this because of this RF, there is some loading effect, some current flow through this. We need to take into account when drawing this circuit without feedback, but with loading effects. So, that is our objective for the next step, right. Draw the equivalent circuit without feedback, but with the effects of loading. Due to the feedback network. Okay. So, that is my goal. Now, this is where the important information comes. Now, this you have to remember, right. A. So, what we are going to do is, we have this, we are going to remove this RF, that is my objective, right. So, that is the feedback element, we are going to remove it, but then when I remove RF, I have to modify this circuit here, where you have that thing, and here, the two ends where it is connected, right. Let us first see how to replace at the output, right. So, how do you replace, or how do you take into consideration the loading effect of this at the output side, right. At the output side, to find output circuit without feedback. Now, this is what you have to do. 1. If you have okay, so if you have shunt comparison, we have already found out whether it is series comparison or shunt comparison. If it is shunt comparison, set Vi to 0. Where is Vi? This is the Vi, right? Vi is applied at this point. So, I am going to connect that input to a ground, right? In other words, short circuit input terminal to ground. That is what I am going to do if it is shunt comparison. And it is in fact, in this case, it is a shunt comparison, right? So, therefore, what I need to do is set Vi to Vi to so this has to be this input has to be short circuited to 0, but this is not. So, my mistake, if it is a shunt comparison, is it a shunt comparison or series comparison? Not shunt sampling, shunt comparison. This is shunt sampling, but series comparison, right. So, comparison occurs here. Shunt comparison, if you have this end at the input. If this was in fact here, you would have short circuited it to ground. But this is not what we need to do, right? This is not what we need to do. What we have is, it's somewhere else. In that case, else or series, if series comparison, set input current to 0, I equals 0. In other words, open circuit the input. Now, obviously, this is a series comparison. What is I? The current that is going through this. Have I marked it? I think I should have. So, the input current goes through like this, right. So, therefore, this current is 0, that means this whole current is 0. So, therefore, what I need to do is I have to open circuit this, right. So, if I open circuit this, what ends up happening is what you have between the output terminal and the ground is this in series with that. So, if I open circuit this, right. So, that is what we have in this particular case. What we have in this case is our case, what you have is RC of the first stage, and then you have you open circuit it, right. This is where you open circuit it, and then you have the output stage, you have this. This is RF, and then you have ground. This is RE1. So, what do you have at the output side? This is the output. What you have here is, starting from here, you have RF and RE1. This is what you need to replace this with. So, therefore, this circuit is that you have. So, this becomes output stage becomes output stage is that's what you have. This is the obviously you have this network, it will be short circuited for AC, right? For AC you can ignore this. So, if you want you can put it here also like that. So, that is what you have in the output side. So, this is what we are going to replace with the output side to take into consideration the loading effect of the RF. B, second part, to find the input circuit without feedback. One, again we look if voltage sampling or voltage sensing set V out to 0. In other words, short circuit V out, output, short circuit the output to 0. Number 2, if current sampling or current sensing set I out to 0, to do that you have to open circuit the output. What do we have here? Right, so let us put this back on. Now we are talking about sensing, right? This part, if this is voltage sensing, voltage sampling, so I am going to replace this part here now. If this is voltage sampling, you have to short circuit this to ground. If it is a current sampling, if you are taking the current sampling, you have to open circuit that thing. In fact, what you have is shunt sampling. So, therefore, what we need to do is we need to short circuit this to ground, right. So, what we will have is we have the first transistor, this is where we need to replace this, and then you have the second transistor, this we are not interested about, C2. What we have is something like this, RF and RE1. What do we do? This is what we have. So, therefore, you short circuit this to ground. Okay. So, therefore, what do we have connected here? We have one resistor RE and another resistor RF in parallel, right. So, therefore, what you have here is the first stage RE1 with RF in parallel, C1, E1, B1. Okay. So, we know how to replace both these. Okay. Remember these two steps. It is not actually hard, it is pretty simple, but you need to figure out if it is a voltage you short circuit, if it is a current you open circuit the other side. Okay. Simple. Number 3, step 3. replace the source with appropriate equivalent circuit, appropriate Thevenin's or Norton's equivalent circuit. Where is my source? This is my source. It's already in Thevenin's equivalent circuit. RS is something, it's not part of the source. Even if it was part of the source, it's still in Thevenin's equivalent circuit, right? So it is already in Thevenin's equivalent circuit. So we don't have to do anything. But if you had some other second, stage here, what you would be doing is you will be replacing that stage with its output Thevenin's equivalent circuit, like R out and AV times whatever the voltage, right? You know how to do that. So this side you replace with that VTH, RTH. RTH in this case is 0, VTH is Vs. So you replace with that. Okay? So you already have it like that with these two modifications. With this, what do you have? This is 10K, this is 0.1K. So therefore, what you have here is a total of 10.1K. Similarly, here this is 10K, this is 0.1K. So therefore, you can consider that as 10K in parallel with 100 ohms is almost 100 ohms, right? Effect of it. So this is 100 parallel with 10K, roughly equal to 100, right? Step 4. Draw the AC equivalent circuit using H parameter model. Now, this is true for BJTs, but for any circuit, you just replace it whatever the appropriate model, right? So let me just say O model or any appropriate small signal model. For example, if you had a MOSFET, still you could have done this. You replace it with its small signal model. If you had something else, it's the same thing. You use whatever the appropriate small signal model. Okay, let's do that now. Okay, when replacing, when drawing the small signal model, what do? We replace the voltage, DC voltage sources with their internal resistance. That means this has no internal voltage thing. So therefore, this has to be grounded, right? And you short circuit capacitors. These capacitors have to be short circuited. So once you have it, you identify that this terminal is the same as the ground terminal, so you can fold over, right? So therefore, what you have is the two transistors. Let's start with those transistors. Let me draw the transistors first. And I'm going to use the small signal simplified version because I know this value is 2.5 kilo ohms, this is 40 kilo ohms. I'm using 4.7 ohms of 4.7K here. This is much smaller than the 40K. So therefore, it's almost 10%. So I'm going to ignore that. So if you want, you can keep it, but it makes life harder. So I decide to remove it. So the two transistors you can use this notation or the notation here, which I have been interchangeably using. So this is base 1, collector 1 and emitter 1. and other side also you have base to collector to emitter to. And then what do we have in between? To the base of my first transistor, you have this parallel resistors. From base, both goes to ground. This is also ground, this is also ground, so they are in parallel. That is R1 parallel R2. And it goes to the source through 100 ohms. Right? How about this side? Emitter goes to the ground through 100 ohms. That is RE1. And what happens to the collector? Collector RC1 goes to the ground. From C1 to ground. And what else? You also have R4 and R3. They are also connected to the ground because this is short circuited, as well as to your base 2. So therefore, this is connected to that, as well as two parallel resistors R3 and R4. This and that. And then emitter of the second stage is short circuited to ground through the capacitor. Collector of the second circuit goes to the ground through RC1, RC2, as well as you have to replace this with whatever you have replaced. Now earlier you replaced this with outside like that. Okay? So you replace that also here. That's the loading effect of this. That's RF and RE1. Similarly, input at this stage, you had a instead of 100 ohms, what you had was there. This was that. So RE1 has to be parallel with that. Okay? So far so good, not hard, right? All what we have done is we have drawn everything as we have. Now this is your final small signal circuit. So you have the output voltage V out here. And you have the input voltage between this. So input is here. So that is my VI. You have to note that this is VI. And this current is IB1. This current is IC1, this current is IB2, and this current is IC2, which is also equal to I, the current that I have marked here. Let's mark this point as the first stage, output of the first stage, and mark this voltage, this whole voltage as V1, some arbitrary voltage, intermediate voltage V1. And Where is my feedback voltage? What is the feedback voltage? Feedback voltage is basically the voltage division between RF and RE, right? Output voltage divided between RF and RE, right? So therefore, my VF is actually here. That is my VF, right? So this is my small signal model. If I want, I can also mark the input impedances and output impedances. Input impedance without the source resistor Ri F dash, input output resistor is let us mark the final output resistors Ro F dash with the with any effect of the loading, and as I mentioned, this is the source, therefore RS is not part of the source, therefore the total input impedance becomes this RIF. Okay. Right. Step 5, indicate X out and XF on the circuit and evaluate beta, which we already have done. We have already done that. So this is my X naught and this is my XF, which we already know, and we have already found the value of beta. X out is V out, XF is VF, beta is equal to XF over X out, that is VF over V out, which is RE1 over RE1 plus RF, which is 0.01, which we already calculated. Step 6. Now it's basically, you have this, it's your thing. So what is this? This can be modeled as a amplifier with Ri, R out and AV times Vi. Now, so therefore, we can find each of these parameters now. Right, find AV, which is defined as V out over Vi, which can be written as V out over V1 times V1 times Vi. So I separate them, stage 1 and stage 2. This is AV1 times AV2 with loading. You can put dash if you want to, with loading. I don't have the dash in my note, so I'm going to remove it, but with loading, with the effects of loading, because when I look at this one, this output impedance is so when I find the voltage gain of this setup, this is already being drawing current from this stage, right? This part is part of the circuit, so therefore it's due to loading from the second stage. So therefore that's why we keep it there. And what is AV1? AV1 is V1 over Vi. But what is V1? V1 is this voltage. This voltage. That voltage is equal to this current. This current flows through this and this path. So these three resistances are in parallel, and that IC1 flows through that path. So that total resistance times IC1 is that voltage. Okay? Because this whole thing I can lump together and put one resistor there. They are all in parallel, right? This resistor, one end is C1, the other end is ground. This resistor, one end is C1, the other end is ground. This resistor, one end is C1, the other end is ground. So they are in parallel. So therefore, V1 is equal to IC1 times the parallel combination of that. That is RC2 parallel, R3 parallel R4 parallel HIE of the second stage. Okay. So that is, so this is what RC1 is 22K, right? So this is 22K parallel 220K parallel 22K parallel HIE is 1.1K. It should be clear that this should be very close to 1.1K. It's a small value, less than 1K. It's about 1K, right? Should be close to that. But if you want, you can find the value. But I'm not going to simplify it further. We don't need to, right? IC1 though is equal to IC1. This current is equal to this voltage, that is Vi. This current. IC1 is HFE times IB1. This is HFE times IB1. Right? So that's the voltage source. What is Vi? Apply Kirchhoff's voltage law to base emitter loop 1. You have Vi, the input voltage, Vi, that is this one, is equal to IB1 times HIE plus HFE IB1, that is this large current, IB1 times RE1 parallel RF. Okay. Mind you, this is the current, this is the voltage input across this HIE. So this is HIE, right? HIE. This is HFE Vi. So this is equal to Vi is equal to this voltage plus this voltage. This voltage is HIE times IB. This voltage is IC1 plus this. This is too small because HFE is large. So therefore this is IC1 times RE parallel 10K, right? So that's here. IB1, you can find the IB1, the current that is going through this IB1 is equal to voltage input VI divided by, using this expression, right? I'm using this. IB1 is here, IB1 is here, so I'm going to divide this by this plus that term, HIE plus HFE times RE1 plus RF. So that's IB1. I have an expression for IB1. Therefore, IC1 is HFE times that, VI divided by HIE plus HFE RE1 plus RF. Therefore, V1 should be this times that. So, I can substitute instead of IC1 this expression. Let us keep that. V1, that is from this expression, V1 is equal to IC1 is HFE VI divided by HIE plus HFE RE1 plus RF times that expression RC2 parallel R3 parallel R2 parallel HIE, that is V1. So, we have V1 divided by V1 divided by VI expression is there, is equal to whatever is remaining after you divide this by HFE times RC2 parallel R3 R4 HIE divided by HIE plus HFE times RE1 plus RF. You could easily replace these notations, these parameters, variables with the real values, and then after that you simplify it and use these numerical values. I am just carrying this because just to make it clear, right? Right. So, this is this value. If you apply all these values, you know HFE is 50, RC1 is 22K, 220K, 20K, 1.1K, and likewise you know these values. If you plug things in, you will get 8.0, minus 8.0. This value should be a negative value. Where did I lose the negative sign? Somewhere there should have been a negative sign. Where was the negative sign? We need to figure it out, but there should be a negative value because IC1, this one, right? V1 should be negative because it should be going out. I1 is coming in, so therefore, so therefore this should be negative sign. Right, thank you. So, you need to give me a value. Right. So, this one has to be negative. Good. So, we have this. Likewise, we can also similarly, for the second stage, we can find AV2 is equal to V out of V1, which is equal to IC2 times, that is the V1, that is the same expression, IC2 times that same thing, RC2. So that is not what you have. IC2 is this. So, IC2 is that, right? This is IC2. So, the voltage is this flows through RC2 and this combination, again negative sign, is negative IC2 times RC2 parallel RF plus RE1. right? This plus this, that is 1, that is 2. So, you have this expression here divided by V1. This is V out, as V out, divided by V1. IC2 can be found using, similar to the previous one, HFV times IB1, which is IB1 is HFV times IB1 is V1 divided by HFV, HIE, sorry, HIE, VI, IB times that resistor there, right. So, you have this expression. So, now it is a matter of replacing IC2 with this expression, with V1 then will get cancelled off, and therefore, AV2 is equal to this expression divided by this expression. V1 cancels off. So, this expression divided by V1, that is V1 cancels off. What we will end up with HFE divided by HIE. Therefore, what we will have is, again the negative sign is there, 145.5, that is AV2. Therefore, AV is AV1 times AV2, which is equal to 8 times 145, negative is positive. So, you have 1164, that is AV. So, now we have beta, now we have A. So, we have D now, 1 plus beta A, right. We can find the value of D. Step 7. From beta and AV, find D equals 1 plus beta AV. Beta A, sorry. Yeah, A is AV, yeah, correct. And the other quantities. Right. So, D is equal to 1 plus beta AV, because A is AV, 1 plus 0.01 times 1164, which turns out to be 12.6. This is D. D is that, you can calculate. So, therefore, we know AV, we know D. So, therefore, AV dash, that is AV with feedback. AV dash with feedback is equal to AV over D. With feedback, that is what we do, right? AV divided by 1 plus beta A, which is equal to 92.1. So, initially you had 1164 gain, it got reduced by a large factor, right? 1000 to 100, like initially it was 1000, now it is 100. So, about this much. So, voltage gain, this is the voltage gain without feedback, but without the effect of this. We have taken the gain as Vi over V out, sorry, V out over Vi, not V out over Vs. Right. So, therefore, this RS is no longer not yet in the equation. That is why this is voltage gain without feedback, but without the effects due to the source resistance. In this case, we do not have a source resistance, but we have put an external RS that behaves like a source resistance. So therefore, we need to take into account later on if you want. It's just a matter of that. Right. So this is AVF dash. If you want AVF, so therefore AVF, which is the actual thing, V out over Vs, which is equal to V out over Vi times Vi over Vs. So that we can find out V out over V, this value is AVF times Vi over Vs, this over that, right, this over that. So we need to figure that out. In order to do that, we need the input impedance. Right. So in order to do that, we'll need input impedance Ri. Now let me calculate Ri as looking from inside from here, right, from here. So let's look at Ri as that. Okay. That is without the biasing network. Ri is equal to HIE plus 10K. So this from here you have this plus these two in parallel. RE1 parallel RF. That's Ri. Correct? That's Ri. This happens to be, if you apply 6.15 K. Just for a sanity check, RE1 was 22 K. Sorry, RE1 was 10 K, right? Times H, so this times HFE. So this current flowing through this is beta times high, right? So therefore, this has to there has to be a HFE here. This current this has to be taken into consideration. Sorry, I forgot about that. Right. So therefore, this value is 6.15. So this value is 0.1. Sorry, this is 1.1. This value should be very close to this RE1, which is 100.1. 0.1 times 50 is 5. 5 plus 1 is about 6. So this value makes sense, right? Value has a sensible value. So therefore, RIF dash Ri times D. Why D? Because now the feedback is in series. When you connect something in series, the impedance has to increase, right? So therefore, we multiply, not divide, by D. So therefore, input impedance with feedback becomes Ri times D, not Ri divided by D. If this feedback was connected at the input side, it would be a shunt connection, then you should divide it by D. Okay. So this value becomes 6.15 times D is 12.6, that is 78 K, 78 kilo ohms. So you have improved the input impedance. So using this, you can now find Vi. Vi is equal to, so this, what you have here is a voltage circuit here, Vi. So I think I have made a small mistake there, but let's see. Vi, so this is RIF. Dash, that's this one, and then you have R1, R2 parallel. So this is RIF, and you have this also. So RIF here, RIF dash, and then, so this should be RIF dash, this should be here, not here, right? Should be one step there. And then you also have the parallel combination of the bias resistors. And then you have the 100 ohms. 100 ohms parallel resistors, RIF, this RIF dash, right? RIF dash, these two together is that. So this voltage, this is the voltage division. Now you have Vs here. So this is Vs times RIF dash parallel R1 parallel R2 divided by 100 ohms plus, so that is 100 ohms RS plus this thing again, RIF dash parallel R1 parallel R2. That would be Vi over Vs. Now, the reason why I said I made a small mistake here, this voltage is not Vi. Vi is actually the voltage across this. Now, what you get here is this voltage, the whole total voltage. So, therefore, if I need to take just Vi, I need to divide it across these 2 volt resistors as well. So, therefore, in my note there should be a correction actually. So, this should be Vi should be this times what you have is HIE RF parallel RE1, this is Vi. What you have here is this whole voltage here, right. So, this is V times you have to multiply by HIE plus RF parallel RE1, right. You have to speak loud. RF parallel, I can't hear you. HFV volume multiply with, yes. This has to be multiplied by HFV. This current is, yeah, correct, yes, times HFV, 2 marks, right, HFV, correct. So, yeah, correct. Now, in my note, I have something a little bit different. So, the values may be slightly vary. So, you need to multiply this by HIE is 1K, this is 1 plus whatever this value, 6, right. This is like, this parallel to that is about 100 ohms times 50 is like 0.5. 0.1 times 50 is 0.5 plus 1 is 6K, this is 6 and 1, 1/6. So, this value will be divided by roughly 6, whatever the value that I have should be divided by 6, right, should be. So, this value I will stop putting the numerical values, you can apply the numerical values, otherwise it is going to give you wrong answers. So, this is basically what you have. Right. So, we know that value. So, it should be roughly Vi should be roughly 0.98 Vs divided by 6. 0.98 divided by 6 is like, I don't know, maybe 0.16 times a Vs or something like that. Yeah, maybe, I don't know. Right, so AVF then, the total voltage gain with feedback is AVF dash, which we found out earlier, times Vi over Vs. This is taking into consideration the source resistance Rs. right. So, this you can find easily, right, because Vi over Vs we already have from here. So, this ratio will give you the value, but I have multiplied by 0.98, but it should be a different value. So, now it will come down even further. Okay. So, that is that. Similarly, input impedance If is equal to Vs divided by II. II, the current that is going through this, and this is the voltage, right. Vs divided by II. 100, that should be equal to 100 plus this term here, 100 plus whatever is here. So, that total impedance is this resistance in parallel with this plus that, okay, 100. So, that is 100 is Rs plus R R1 parallel R2 parallel HIE plus HFE times RE1 parallel RF. Not parallel, this should be, yeah, it should be parallel. Yeah. So, whatever that is your input value. I have a value of, this should be fine I guess, but I don't know, maybe it's wrong, but the value I get is according to this equation that, but double check, okay. This may be wrong, it may be correct also, it may actually be correct. And current gain with feedback is another quantity that you may be interested in, is minus I over I1, I in. Output current is I, it is a negative current going out. So, coming in is negative, going out. I input is I1. So, therefore, this is the ratio is minus IC2 over I1, II, and you can find it out by, let us write equations with these expressions. We know V out is equal to minus IC2 times this whole thing, right. So, that is RC2 parallel RE1 plus RF, that is V out. Vs is equal to II times RIF, that we calculated just before, because what we are looking at, this is connected to some input impedance RIF, right. So, including the RS in there. So, that is that. So, therefore, AV F we know is V out over Vs, we already calculated this. Sorry, not V, what we want is I. Sorry, no, what I, this is AV, right, this is correct. AV is AV with feedback, which is equal to V out over Vs, which is equal to minus IC2 times RC2 parallel RF plus RE1, that is this one, divided by I1. So, this is the expression for that, is equal to I1 II times RIF. Now we have this term here, which is what we are interested about, right? This is the term we are interested about. So therefore, we can find so this is AIF times this term, AIF times RC2 parallel RF plus RE1 divided by RF. So that's all these terms are known. You can find the value. The value that I have is 314. Probably it is wrong because I have made a small mistake in calculating the input value. Right. So that's that. The last quantity that we are trying to find is output impedance with feedback, ROF dash, which is equal to RO dash. Now we are putting it in parallel. We are putting this in parallel. What should happen? Should reduce. So therefore, you divide it by R. Okay. What is R out dash? These two combination. So R out is basically R out dash is this. R out dash is that. So R out dash is RC2 parallel RF plus RE1. That's this term divided by D. That's the value you will get. I think the value is 253 ohms. Right. Remember, here is R out without feedback. Here is R out with feedback. Okay. Any questions? Okay, this is basically what you have to do when you see an example, exam question like this. Now, typically this takes a lot more than 30 minutes, as you can see. So you won't be asked to do this whole thing in a one example, but if you have looked at previous exam papers, you have actually done this within the exam. I have broken this into multiple questions without having to depend on each question, giving, sometimes I ask, okay, derive this equation for a single stage, and then you put multiple stages, what is the total gain, and then if you add this additional feedback, how it changes, right? So likewise, I can do that. So in the previous exams, if you have seen, you have actually done all this within the exam, but under different questions. Sometimes people don't realize that it is just one question, right? But if you, with this knowledge, you might actually see. So you can actually use information from the previous questions for this, right? The remaining 10 minutes, I would like to give you a few other example circuits, and let's try to identify what is the topology, what is beta, and things like that, right? What we need. Okay, ready? Any questions before we start? Okay. So here I am expecting you guys to actively do some things and write down. So I am going to come down. Okay. All right. Hopefully this is done and over. Okay, at least one or two examples, let's try to do, okay? Right, the first one. Simple circuit. Like this. Okay, so the values are 10K, 100K, this is RE. This value is 1K and this is IS. Output is taken from here. Yeah. Okay. So, what you need to do is identify topology. How do you identify the topology? You look at the mixing circuit, whether you identify the feedback component, identify where it is connected. If it is directly connected at the output, it's a shunt mixing, shunt sampling. If it is directly connected in the input, it's a current mixing. If it is not directly connected into the input, it will be a voltage mixing or shunt mixing. And output, if you don't have the one of the ends directly connected to the output, it's a series sensing, right? So, likewise, what is the topology? So, likewise, you can say series, shunt series, or voltage series, voltage shunt. Likewise, you can say, and also find the XF and X out and beta values, right. So, that is for this one. I am going to give couple of these. So, you can try this and go to the next one if you are successful. Okay, we will see. Now, this shouldn't take more than 5 minutes. The first one, it will take time because you have to identify, but later on, once you learn how to do it, it should be very easy. Again, topology, X out, XF, beta. I think we might not have too much time beyond these two, but I will write down and give another one. Don't even take it down right now. Try to do this. Focus on doing at least one here rather than taking down. All these are available online in the notes. So, therefore, try the first one while I draw the last one. This one is going to take long to take down, so don't take down. So, it's basically the same circuit as before, but feedback is connected to a different place. you have any issues, you can ask. Remember how you figure out? Look at the output. If the output is, determine whether the output is a voltage. If you are sensing the output in shunt, that's as if you are using a voltmeter, that should be a voltage output that is measured in shunt. That's a shunt comparison. If you are mixing it, when you are giving the feedback input, if you are connecting it directly to the input, that means you are shunting it with the input. So that means you are adding two currents. So it should be input should be a current. So mixing should be shunt for currents. If not, the other way around. Okay, so it's easy. Identify the feedback element first, and then you can do that. Don't worry about the last one. Try to do the first one. If you can do the first one properly, you may be able to do the others. Correct. Mark the currents and what is IF and IOT. Check what is the input and what is the output, and the type of signal feedback signal should be the same as input signal. Output should be a voltage or a current. Input should also be a voltage or current. Feedback signal is the same as the input signal type because they are mixing. So that you can double check, it's also here. Here first the topology, sampling is in parallel. So it should be a voltage output, right? So this is a shunt or voltage output is a voltage that we measure using shunt, and the connection is directly in the input. So therefore, input is a current and connected in shunt. So therefore, this topology is a shunt or the other notation voltage shunt, right? Shunt. So what is the feedback element? Obviously, this is the feedback element. Since this is the IF should be like this, right? IF should be like that. So this is IS, this is II, and this is output voltage V out. So therefore, X out obviously is V out. That is what we sample. We have already indicated what is the feedback signal is IF. So this is IF over V out, and this is easy to figure out what this value is from this circuit, right? So it's basically, you will see that this value will be close to. So you can write IF is equal to minus VI minus V out divided by IR, RF is RF, right? So, but we know that VI is very small because we are amplifying. V out is AV times VI, right? So therefore, V out is much bigger than VI. That's what it does, right? So therefore, this voltage difference is pretty much the same as V out. VI can be ignored, but negative sign is there, divided by this RF. That's your beta, right? And then divide by beta, you will have 1 over RF as your beta. So that's easy. What is the topology here? Where do you sample? Where's the feedback element? This you have been seeing all along, right, from the beginning. What is the feedback element? Not this, not this, not this. The only one possibility. This is the feedback element, right? So this is RF. So therefore, what should be the output is clear. So this element is not directly connected to the output. So therefore, output is not sampled in shunt. So therefore, it should be a current. The output is a current. Current output, current sampling or series sampling. And what is the input? It's not directly connected to the input. So therefore, it cannot be a shunt comparison or the current. So therefore, input is not a current. So input should be a voltage which is mixed in series. So therefore, the topology should be series, right? Input, outputs, series, or current series. Input is a voltage, output is a current, feedback is mixed in series. What is the output? Obviously, as I said, output is a current, so the output is not V out. Output is this current, I out. This is the current. What is the feedback signal? This is in the input circuit. So therefore, this is your VF. VF is the feedback signal, and VF divided by I out. Obviously, this voltage is equal to Vf is equal to Rf, whatever that voltage resistance times I out. So, therefore, this ratio is already there. So, Rf is the feedback factor. But there is a negative sign though, right? Negative sign because current is coming in. If output current would have gone out. So, therefore, the negative sign is there. How about this one? Now, one note before I move on to this, just 5 more minutes. When you draw the equivalent circuit, remember the input is this across the emitter. So, therefore, when you draw the equivalent circuit, you have the circuit like this, right? So, this is the base collector emitter, this circuit, and then you have this is there, these two, sorry, this and that. So, this is basically R1 parallel R2, this is RC, and then of course you have this source, and if you have a load there, is there, it's not there. So, therefore, it's like this, right? Now, because this is in fact the feedback network, you have to then figure out how do you load it, how do you draw it without the loading effect, without the feedback but with the loading effect. So, for that, first thing we see one side is directly connected to the, so if you look at this, if you want to figure out the output circuit, you look at the input side. Is the other side of it, is it connected to the, directly to the input? No, it is not. So, therefore, what do you do? You open circuit this. So, therefore, when you replace the output circuit, that is this circuit, this should be just RF, right? RF is between ground and the ground and collector resistor here. So, the ground is this. So, what you will have is something like this, RF. Okay. Similarly, if you look at the input circuit, where is this connected in the output circuit? Is it directly connected to the output? No, it is not correctly connected. Then what you do? You open circuit it again. So, you open circuit once again, what you end up with just that same thing. That means you between the ground, this is the ground, and the emitter, you have this again. So, this is how your equivalent circuit would look. This one is pretty much similar, except that feedback is not taken from here, or feedback is not given here in the previous example that we worked out. So, it should be exactly the other things. Right? If it was voltage series, now it should be current shunt, right? Output is a current, that is why we measure it here. You connect it with shunt. So, this should be a current shunt topology. What is output? Obviously, that we said it's output I out. What is I out? This current I out, right? That's current I out. What is XF? XF is the current that is here, it's IF. This is IF over I out. So, you need to figure out, once you draw the equivalent circuit for that, there should be a current divider, voltage divider for the previous case. Now, you have a current divider. This current should see two paths. One path is this, the other path is this combination, right? And then according to the resistor ratio, you can divide the currents. You know what IF is, you know what the I out is. Sorry, so the current ratio between these two, you know. Okay, right. So this is where we are going to stop, right, for this series. I have already uploaded 2 tutorials. Please try them. You should be able to do it. If you are not able to do it, discuss among your colleagues. That's perfectly fine. And try to answer the questions on your own. Don't copy, it won't serve any purpose. The fact that these questions are there means you will get similar questions in the exam. If you cannot do those questions now, when you don't have the pressure of the exam and when you have infinite amount of time almost, right? Unlike this pressure under 30 minutes or 1 hour or 2 hours, you should be able to do it. First time you may not be able to do it, but that is fine, try. And you should be able to do before the exam, you should be able to do them. But there is a deadline sometime, I don't know, I can't remember. Submit the answers, just upload the answers, what you do, scan it and upload, right? So that should do it. And I will post the answers after that. Any questions before we wind up? Okay, today afternoon you have the design class. We'll see some of you there. The others have a look at the video that I have uploaded for the design. I have also uploaded one of the videos, previous videos on 26th one, January 26th one onto the YouTube. I have included in fields as well. The sound quality is not that good because I think I have forgotten to switch on the mic, but I have tried to improve the quality. It's kind of okay, but it's a little bit difficult. But those who are here should find no difficulty. Okay, then good luck with your course. From Monday, Dr. Ratnayaka will start his section. Thank you.